I feel like it is wonderful. Um, so yeah, I will talk about large language model pre-training on Google Cloud Platform. And here's the saddest group presentation ever, since it's only me as being part of this project. But the background is that I'm an industrial PhD student at Bonnier News, which is the Nordics' largest media group, news media group. And the aim kind of for doing this project was to try to use Google Platform, Cloud Platform, which is our internal usage. So that's everything is on GCP. And here are some numbers just about when we started. It's like 200 different brands, from newspapers to like weekly magazines and stuff. 2,500 journalists and 6 million, I think it is daily readers/viewers/listeners. So what I wanted to do was to create one unified pipeline for both creating a pre-training data set from raw news article data, as well as then use that data set to continue pre-training a large language model, which I will explain a bit more next slide, I think, even though it's pretty self-explanatory what it is. And I also wanted to utilize distributed or scalable techniques to be able to do it for arbitrarily large data sets and model sizes. Like not arbitrarily in reality, but to some degree at least. And I also wanted to do it using multiple different tools and frameworks and not just using one framework from end to end, because there are a lot of tools, and I'm sure you see them as well, where you can input basically a text file and then out comes a model, and you don't really know what's happened. And I also wanted to try to use Spark in some sense, since we used it a bit in the course previous, and then do it on Google Cloud Platform, as I said. Okay. So continued pre-training, it's basically what the name says. You take an already trained large language model and you continue pre-training it on new data with the purpose of trying to specialize it or adapt it to something, which could be a new language. You want to incorporate new language and new knowledge or updated knowledge. You want to specialize it to your specific domain. It's very common to do for like medical or legal stuff, which is super specific around language and the kind of knowledge you want baked into. Or if you wanted to become better at a certain task like coding or problem solving, for instance. And it's super simple. It's the same like prediction objective with the same training loss that you have for the original pre-training. So I guess most of you know how LLM pre-training works. You have a sequence of tokens and you try to predict the next token. And that's basically the entire foundational training part. And that's what you want to continue doing. And the idea is that you can use a lot less data and a lot less compute to specialize a model rather than training something from scratch, which is very expensive with a lot of resources. So we want to kind of incorporate new knowledge while also trying to retain some of the general knowledge that's already in the model. And so conceptually it's super simple, and what's challenging is the small details, like the data mix you're using, like how you're warming and scheduling your learning rate, and what parameters you're updating and such. And that's what kind of trades off incorporating new knowledge versus forgetting old knowledge. So a bit about Google Cloud Platform. It's Google's suite of cloud computing services. It's basically the same as Amazon Web Services or Microsoft Azure. They seem all the same. They have mostly the same products, to be fair. And I've used mainly 4 services, you could say, in this project. One is just cloud storage, which is the blob storage for just storing files and stuff. Then BigQuery, which is like a managed data warehouse solution for running SQL queries over structured data. Dataproc, which is kind of the Databricks of GCP, you could say. So you can run like Spark jobs, Hadoop jobs, like Flink jobs. And then what's called Vertex AI, is a very fussy name for like everything AI related that they have. But I specifically used something called AI pipelines, which is a way for running or orchestrating machine learning. And my view of GCP and AWS and Azure as well is basically that they try to productify open source frameworks. So all of these are kind of built on open source software, but they offer it in a serverless way and managed way. But a lot of the techniques can be applied to any of the other services or like self-hosted environments as well. So to create this kind of end-to-end pipeline, I've used what's called Kubeflow pipelines. Has anyone heard of that before? Okay, so it's basically a way to orchestrate machine learning workloads using Docker containers. And that's basically it. So you define your job or your pipeline in terms of connected components, and then Kubeflow figures out how to create a graph of that, and then handles all the scheduling and like dependencies between the components for you. And it's typically deployed on Kubernetes, which we talked about. We have talked about it a bit, I think. But basically just a scheduling framework for containerized workloads. So yeah, a pipeline is basically a DAG of components, and a components is just some smaller task of the pipeline. Like if you want to do it really simple for yourself, but also in the end maybe more difficult, you can have one component that's the entire job. But typically it's a smaller subtask, and that subtask is self-contained with like a bit of code and a Docker container that you point on. So you have like a self-contained little package of code that's running. And the idea is that you can combine components from different pipelines to create different kind of workflows as you go. And between each component, you typically produce some artifact that you're forced to write to disk or to blob storage in this case, which is super good for debugging and traceability, and also for caching. Because if you have the same input to a component, you always get the same output. They're considered deterministic. So if you run a pipeline and it fails midway through and you run it again, it just caches all the outputs, and you can look at like each intermediary step. So yeah, very traceable, composable, and also scalable. So for each of the components, you can kind of choose what machine configuration you want. So I thought maybe we can just look at how a pipeline looks like. It's working. Slowly to begin up. Okay, so these are basically components which have some inputs we see here, and then typically produces some outputs, which in this case is like a table you can actually click on and link to. Yeah. And then you kind of chain them together. And typically also artifacts have a link to the blob storage. So an artifact is mostly a file for multiple blobs. Like here, it takes a lot of Borggren Lukas. And this is kind of the DAG that's built up by and then here's a component that's being cached as our model. Yeah, so now I would just walk through what each component here is doing. So first off, my use case, as I said, is news articles. And the first part is a bit stripped down for the purpose of this because it involves a lot of like proprietary structure on like where we store data and what kind of metadata and stuff around it. But this stage is basically to try to aggregate data from multiple sources and try to filter out data that we know we don't want to train on For instance, if you've seen kind of news article that's like sport results that are written according to like a formula, or like real estate sales in like your municipality, they're all based on like robot texts. So those are kind of easy to filter out. At least the new ones. The old ones maybe not that well tagged, but hopefully later parts of the pipeline will be. And this is done in the data warehouse using SQL. It's completely serverless and super scalable. I'm not sure what's used on it actually, but it's super fast and you can do a lot of stuff. And the results from this part is just moved to a new table, which is then consumed in the next stage, which is the exact duplication stage. So even though articles may have different IDs or unique identifiers, they can have almost the same texts because of, for instance, cross-publishing. So one newspaper might publish a news story in, I don't know, in Skåne, and then in the other part, the same story is published, but for a different newspaper. And depending on when they were published, sometimes they don't reuse the same ideas, so you want to filter out those. And I did some like simplification of the text before doing this exact duplication. So it isn't really exact. Basically some kind of normalization of the text, Unicode normalization, lowercase, white space normalization is a big thing because certain articles just differs between how many steps, like a new lines. Some have one, some have two. And if you normalize all white spaces and new lines and tabs to just a single space, you can remove a lot of data actually, especially older data. And then also try to remove some diacritical marks, which is basically to have apostrophes or like the dots over O, because they can be encoded depending on when the article is from which system it really came. And this is done using PySpark on the Dataproc service. So it's very similar to what we did in Databricks, apart from it not being a notebook. We kind of submit a batch job to a Spark cluster that's managed and completely serverless for you. And then you can have some parameters that's controlling how much replicas and how much auto-scaling you want to enable. And yeah, super fast transfer between like the data warehouse and Spark, which was kind of crucial for this stuff. Because if you want to download all text from BigQuery to local disk, it can be super slow. But here I think what it does is that it creates the partitions when you query the table like instantly. So it just shards the outputs to multiple worker nodes immediately. So it's super fast. And then the next step is fuzzy duplication to try to remove stuff that are not identical, but very close to identical. And this is a very slow process, especially when you have a lot of data, because what you want to do is basically compare all text to all other texts. And then if they are sufficiently similar, you want to throw away one of them. So to do this, I use a technique which is very common called min hash, locality sensitive hashing. Which is basically a way to approximate similarity, a similarity measure. And it's based on having some representation of the text, which is usually like n-grams or shingles. And then you kind of, over the vocabulary, you create random permutations and create, for each permutation, you create kind of a hash value. And you do that for a number of times. And then you get like a new super dense representation that I think it's theoretically proven that it kind of approximates Shepard distance. So we have a set of tokens and you want to see the overlap with another set. And lucky for me, PySpark actually has an implementation of min hash from their MO lib, which I used for that part. And then also when I had the pairs, I also wanted to cluster the pairs. So it's, for instance, if A is similar to B and B is similar to C, I want to create a cluster of A, B, and C, and then retain only one of the articles from that cluster. So doing that, I use what's called graph frames, which is basically what's called GraphX in Spark core, but there's no Python API for it, so it's a third-party library. So I created a graph of all of the connections between articles, which was like if they are sufficiently similar, and then I find the connected components in the graph. And from each connected component, I only retain one of the articles. And this is also on Dataproc and written as Parquet files as well to the blob storage. And yeah, then I just have one component that downloads the model, which is not that interesting, but it's mostly for like networking reasons, because each component necessarily doesn't have an internet connection, or not an internet connection to the web. Maybe it's trying to be connected to other things within the cloud platform, but not to the web. And also because of authentication. So there's only one component that needs to know, like my Hugging Face token in this instance, to download a model from the hub. Then I also actually tokenized all the texts using PySpark as well, which might be a bit unnecessary, but it was kind of fast and easy to implement to create just one user-defined function that performs the tokenization. So you don't have to do that every time you start the training, which some frameworks want you to do. Like it's part of the loading the model, loading the process that is tokenized. But that can be super slow if you have a lot of data. And again, save as Parquet files, which is then loaded by the training components. So one issue generally with large language model is that you almost have to do it in a distributed way. It can be because the model is simply too big to fit into one GPU, and also that you want big batch sizes, and that the sequence length are super long. So you kind of have to do some distribution of the work in order to make it work at all. So the idea was to do it across multiple GPUs and possibly also multiple machines or nodes. And I guess some of you have dabbled a bit with this, but there's a lot of different frameworks you can choose from to do kind of handle the distributed part for you. And also that gives you some boilerplate code for like checkpointing and stuff. And in the end, I opted to use which is called TorchTune, which is basically a PyTorch implementation of a lot of like popular open LLMs. So they're kind of broken it down and written it all in PyTorch. And it's a super useful library because it doesn't have all these abstraction layers of, for instance, PyTorch Lightning or Accelerate that has like 5 classes that inherit from each other. It's very easy to just reuse modules. And then they have, for some types of training, they have recipes which you can kind of extend that implement some kind of tuning. And one of the cases is like regular pre-training. And TorchTune also uses what's called Torch Run, which is just a way to run Torch training in a very scalable way. And then Torch Run handles all of the like environment variables for nodes and IP addresses and stuff. And also use what's called PyTorch data flux, which is basically a way to write stuff directly to the blob storage from Torch instead of first saving it to local disk and then saving it to the blob storage. Because if you have a big model, that can become quite of a blocker if you want to save a checkpoint, and then all processes should wait for that saving, and it can take a couple of minutes. And TorchTune implements what's called fully sharded data parallel, which is basically one of 2 ways that I know of. The second is deep speed, where you try to shard like everything during training, like the model weights, the optimizer states, the gradients, and also the data. So it's basically 2 different things of doing it. Some prefer deep speed and some prefer fully sharded data parallel. And then also you can train in like mixed half precision, which is kind of standard. So you just reduce the how much space each number is taking up basically in the processes. And yeah, then there's a lot of other optimizations that you can like trade off memory usage versus speed. And especially memory is the crucial part. Like all of the gradient checkpointing, gradient offloading, gradient accumulation, all of those are for offloading the GPU memory and kind of ditch stuff that you maybe know you want to recompute. If you ditch them from memory, you can fit more stuff into memory. And then instead you can take the recomputation costs in doing certain calculations. And this is run as what's called a Vertex AI custom job. And this is actually the same as for the Spark workloads as well. So these components are not really, I mean, they are self-contained, like small code snippets, but they basically just start another job, which for the Spark cases, it's just a Spark batch job. And in this case, the component is kind of that you just start a distributed job. But then the components is just like a shell around it, so you can connect it to all of the other parts. And then you can basically ask, so for each of the components, you can kind of ask for the hardware that you want. And in this case, you can, with the custom jobs, you can define multiple worker pools so that you have, for instance, one like a parameter server that has one configuration. And then you might have another group that does the actual training that can have a different set of configuration with GPUs. And I don't know the limits for scaling this, but if you have like enough quota in your product to use a lot of NVIDIA H100s, you can do it. I didn't have that, unfortunately. I guess there is some roof with how much you can do if you're like a regular customer, but theoretically, you can kind of increase the number of workers and the number of GPUs per worker quite a bit. So the results are pretty interesting, to be fair. I didn't have the time or frankly the money to perform something super large scale. So I did it with 100,000 news articles, like all the way through the pipeline. And 1% of the data was removed. And I would expect it to be a bit more, which I think I will see if I have more data, because then these clusters that I create will become larger, and you will throw away more from each cluster because it will be bigger. So instead of 3 articles, there might be a cluster that's 15 articles, and you keep on doing one of those. And I used a super small, in this context, Llama 3.21 billion model, which is like the smallest you can go. And I didn't do any rigorous hyperparameter tuning. I kind of made it work with the memory requirements I had and just checked that the training code was doing what it's supposed to do, which is the loss training loss up to the right. And yeah, seems to work. And I just did that train for 2 epochs to see that all of the checkpointing and stuff worked out. And then also you can, how many have used TensorBoard here? Yeah, cool. So you can kind of as well upload your TensorBoard logs to Vertex AI as well. So you can, yeah, check out the training progress, which is kind of neat.
The Llama 3.2 is
I think it's mixed, but mostly English. Yeah. They don't really disclose the exact mixture, but predominantly English. Yeah. And I think it's optimized actually for like edge case users. So having it on like your phone or something. So they might have done something to it that may be that it's not the best thing to continue pre-training. But it has the same architecture as like a 7 billion parameter model. So yeah, future improvements, which I have a lot of. I think the turtle is, for me, being maybe slow or biting off a bit more than I could chew. One of the things is like performance tuning in Spark, which was surprisingly difficult, especially with this min-hash LSH algorithm, which became super slow with certain configuration, which I think has to do with how you're kind of embedding chunks into these different hash values. And it was kind of hard to study the implementation, like how it was done. So that's one thing I would like to do more of. And also would like to have, in terms of like a scalable setting, have a streaming data set, which I didn't have the time to implement. Or Torching doesn't support natively. I didn't have the time to extend it to handle it. So the idea is to have data set on the blob storage, and then you stream the data as you need it to the training processes. So you never download the training data to disk. You only stream it from the blob storage, which is more efficient. And also, I didn't actually get multi-node training to work, where you have multiple machines because of networking configuration issues. I realized after debugging my code for like 2 days straight. So that's always frustrating. And I want to do more evaluation because, as you can see here, this is only the training loss, like no validation loss or like perplexity metric or anything else. Perplexity is like a regular way to measure how well you can do progress. And in some use cases, you also want to do the same for like the original pre-training data, if you know what it is, kind of, so that you don't degrade the performance too much on the original data, which is typically an indication that you're like overwriting too much of the original capabilities. And it would also be fun to try out other training frameworks. I tried out PyTorch Lightning for this Torch team, and also a bit of Accelerate. But then there's also like Megatron framework, and they all kind of do the same thing but in different ways. So I think it's just a question about preference and trying out what suits you. And I think that's it. Yeah, thanks. Oh no, you have to pay the thing. Unfortunately, I mean, you can set up like a Google Cloud project for yourself, and you get like some free credits. But I'm not sure like if you can use them for anything or how much it actually is.
So you mentioned that you have your scripts and you can use Scribble to analyze it, but it was a bit intentional. What benefits they could bring was it the resources?
Yeah, so essentially they host the Kubernetes cluster, and you don't have to care about it. And what you submit is the Kubeflow workflow, which is basically is a YAML or JSON file that specifies each of the steps and the resources you want, with some code and also like a Docker container that's in the cloud. And then that's the only thing you submit, and then just Google handles it. And you get all the caching and saving artifacts to the cluster. Yeah, or the news articles are actually in the data warehouse already. So the first part, the like aggregation part, is just grabbing it from different sources within the data warehouse or the data lake.
There be any like meaning to when you choose the articles? I assume you choose there were articles of all time or all time. There be any point in like one time just picking this sport article, or like instead of doing this kind of global on news, like doing a specific?
Yeah, it could be, but usually more is better in the pre-training phase, and like having it like in Swedish and having like news text is kind of already quite niche in the context. But then if you want to build something on top of it, maybe you just want to use sport articles for that, for instance. But typically more data is better.
The typically a later.
Yeah, I mean there are like previously there were like pre-training, fine-tuning. Now there are maybe 4 steps, like intermediate training or like post-training. Yeah, with like instruction fine-tuning and preference tuning, and like maybe training for getting a longer context. Yeah.
Following question on Kubeflow. You mentioned like number of libraries or frameworks you have used in this pipeline. So how was it like? I understand how it kind of maybe linked by Kubeflow, but how did you make the decision along the way, like choose this specific like PySpark or TensorFlow? Is it a template or recommendation by Kubeflow platform, or
A bit of both, I would say. So the good thing with Qubit actually is that since it's just a container that's running some code, you could theoretically run anything in that container. It doesn't have to be even Python, which is what I used. You could have like an R script doing something, like some Java code doing something else. But in terms of the framework, Torch is just what I'm familiar with. And I use TorchTube because it's native Torch and it's specifically designed to not be super convoluted in terms of having different trainers and like model classes and data classes. And PySpark was basically because I wanted to try to incorporate Spark somehow into this pipeline. And then TensorBoard is something that it has support in this cloud service, which is why I used that. So you can create an instance in the cloud, which gives you like a directory to which you can log your progress, and then it shows up in the like graphical interface.
Other quick questions regarding the training epoch. You only train the twice, 2 times. Is that because it takes too long to complete a long epoch?
I basically chose 2 just to see that all the checkpointing worked. Normally you would typically have that much data that you maybe don't even run an entire epoch over the data. It depends a bit on how much data you have. But like if you pre-train from scratch, it's very common to not even train a full epoch over the data. But if you have less data, maybe you want to train multiple epochs. So yeah, the reason for choosing 2 is the minimum one, which I could see that all of the like intermediate steps after an epoch actually works. And it worked out like at reasonable scale. So the idea would be that you could, if I get the multi-node train to work, that you could do the same thing for like a 7 epoch. And it should be fine if you have the enough hardware. Yeah. No, I didn't have time to implement that. But that's typically what you want to do. So when you've trained your model, or maybe after each epoch, you can both try to like measure perplexity on the original data, or if you have benchmarks, like both general benchmarks that the model should be good at, and that you have like a number from the actual pre-training, and then you have some other benchmark that's measuring how well you're doing on like, your specific domain. Typically want to monitor those like together to see that you're not like regressing performance that much from the original benchmark as well. Yeah. So about actual setting a threshold for when things are like sufficiently similar, a bit of a hunch to be fair. There's no clear guidelines of like how to choose that. You have to look at data and see what am I filtering out when I have this kind of threshold.
You have a 100,000. Is it 1 hour to take a 1% of the
That's what the PySpark implementation of min hash does. It removed 1% of the data. So in this case, just 1,000 arguments. But you can kind of tweak that to trade off like the dataset size and how certain you are that you have clean data. And it has some like theoretical properties, which if you have certain settings for the min hash algorithm, you can say that if 2 articles are like 0.9 similar, we're 99% guaranteed to actually filter those out. So there are like some theoretical properties that you can use to kind of treat it. And the more rough you are, the faster the algorithm runs, of course. So typically you do less permutation of the hashing, and then you don't have to compare too many. Yeah, like arguments basically. But there are certain different ways of implementing it, and PySpark did it in a way that I never saw. It was a bit confusing. But it's a very cool technique if you want to deduplicate texts. And if you have like a couple of 1,000 articles, it's very easy to just run on your laptop.
Yeah, I mean, I have some recent experience with Spark's implementation of main hash in the family of LSH, locality system hashing algorithms to use pairwise distances among strings basically. So in your case, article, if you were looking at call detail records for Sweden, so like cell tower signals, like one device is getting the so there, I think performance. You have all these parameters to do like the sampling rate of the algorithm itself, but I guess one tip to improve it would be if it's slow, you may want to look at the number of partitions.
Yeah, that was the first tip when we started Googling.
Yeah, and if it's 200, I think it's still default 200, right? So it's not the power. Then it definitely something is wrong.
Yeah.
So stupid thing to just change it to 100 or 400, but the basic theory is all about making sure that the number of partitions is such that you're not having stragglers and blockers, right?
Yeah.
So
because I'm not exactly sure how the computation works, but you can kind of discern looking at the computation graph from Spark that there's a lot of like all-to-all communication, even though it's not actually doing exactly pairwise distant. There's a lot of communication overlay. And then if you have a lot of partitions, there will be a lot of.
that's good. One quick question. So I guess this is some kind of a product that one here is going to try to release or something. You don't have to talk about it.
And not a product really. It's mostly for my own research, to be fair.
Okay.
And maybe I don't want to actually do this on GCP. Maybe I want to do the training part on Berserkers, for instance. But it makes sense for Borggren as a company to be able to do it on GCP as well if they want to train I want to train more stuff that you can't really use Berserkers for, because it wouldn't make sense because you want to do the same thing with like more data, and maybe it's not connected to research. So this is just a way to see how can we do it on Google Cloud Platform. And then when actually producing the research result, probably you would do the training parts on Berserkers.
I guess where I'm trying to go, this is, I don't know if you know ground.news.
No.
Yeah, I don't know. Anyone knows about ground.news? I highly recommend it. So it sort of gives you the media narrative, right? So it's one company, it's something similar in the US and Australia, like one or two companies own a whole bunch of media stuff. Anywhere from very right wing to very left wing to very conspiracy theory. So ground.news gives you these flags. Okay, this is like a school of thought or whatever, right?
Oh yeah, I think I've seen that. Yeah.
Yeah. So I don't know. I'm just curious because you could kind of play the same sort of game here, right? And so that you could train eventually something that would look at. So you could ask questions and say, what would a Swedish Democrat say, or would it be a typical social democrat response on a topic, right? I don't know, the same issue.
Yeah, it could be.
To like have some kind of AI assistant to interrogate different ideological forests of Sweden.
Yeah, there's a lot of discussion about, like, as you've all seen about it, like interacting or like chatting with the content we're doing different stuff. And asking for different viewpoints could definitely be one of those things.
Okay, so there are no other questions?